So good morning. We look at the concept of reflexivity and possibly at the concept of what are called annihilators in this talk. Let us begin with reflexivity. Let us recall what we did up to now. So V is a vector space over F of dimension. This is our starting point. Then we have looked at the space of all linear functions, which we denoted by V prime. V prime is the vector space of associated with V of all linear functions over V, and thus we designate it by the symbol V prime. And then we prove that dimension of V prime is equal to . So there are several isomorphisms between these two n-dimensional vector spaces. Now, if V prime is an n-dimensional vector space, why not we play the game again and look at all linear functions defined over V prime? That also is going to give you a linear space of dimension n by repeating the arguments that we used in the construction of V prime from V. So let us designate, it is self-evident that we have V prime prime. V prime is the space of all linear functions over V. And V prime prime is a space of all linear functions over V prime. And then you know that this is a vector space over F, again of dimension Now let us use some notations. We use script x as an ordered basis V. Then we denote by script y where yi delta I. But this is for one to n. This is what you call the dual basis. So x is a given basis, y is the dual basis of V prime associated with the basis x. In the same way, one can construct a basis which is the dual to y in v prime prime, and v prime prime we conveniently designate by v double prime. Okay. Okay. Then Z, there exists an ordered basis Z1, Zn in V prime prime such that it is dual to this one. Therefore, you have Zi Yj equal to delta Ij. So these are the notations for that. Now x script x is an ordered basis for y is dual basis, and set the dual basis of Now what we observe is the following. See, you see that for a given y of x is in x. Okay, that means there is a functional defined on V by the function y of x, and y is a functional, and if y is also chosen such that y is linear, then it's a member of V prime. Okay, so you have yx now. Switch the role of x and y and look at this as allow y to vary, fix x and allow y to vary. Then that also defines a functional on V prime. Okay, so fix x and vary y. Then it defines a functional over V prime. Now the question that you ask is this a linear function? If we could prove this, then you see that x defines a linear function over V prime, therefore it is in V double prime. Okay, if yes, then x defines a So we look at this, we explore this question. Okay. So we define the following. So let us Z be defined on V double prime by Z of P. Then Z is a functional on B prime, and now we prove that we shall see whether Z is, just investigate this. So this is what we are checking. So first thing that we try to verify is this. We have Z of Y plus Y tilde into, by definition, it is Y plus Y tilde of X. And this, you know, is equal to Yx plus X. And this, you know, is Z of Y plus Z of Y. This is true for every Y belongs to V. So Z is set. So we verify the second fact whether it is homogeneous. So let us verify this. So Z of alpha Y, this is equal to alpha Y, this is by definition, and this is equal to alpha of Y of X, which is equal to alpha Z Y. So Z of alpha Y is equal to alpha of Z Y. Therefore, what we have is that it is homogeneous. Therefore, Z is now by by 1 and 2, is a linear functional over A. Hence, which means that given an x belonging to V, it determines a unique element in V double prime. So this is the picture that you have. So this is the picture that you have. This is V prime. This is V. This is V. Start with the x here. Take a y here. Now what it does, suppose this is, so you see that this essentially this is y of, this is y of x. Now what one does is that z is defined in V double prime, okay, picture. It's like this. So you have y here. This is the y of x equal to is an element of f. Now what one does is, see, you identify or this essentially defines a element z in V double prime through this track. Using different color to display this. Okay. So this is one track. Now what you can, so you see that there is a connection between, for each x there is a uniquely determined z, and this is also equal to, this element is actually y of x, this is also equal to z of y. That is the connection. So now what we are going to do is, so you see that for each x determines a z here. Therefore, let us now define a map from x to z in the following way. So each x determines a corresponding z in V double prime. So this. such that y of x or z of y now this is the basic definition of z, and we have seen that z belongs to V double prime. That's our definition. Now what we investigate is this. You look at the map which carries x to z under this condition. Z whenever z of y equal to y of x. Now you know that this is well defined. Y is well defined. Y is well defined. It is defined for every x belonging to V. At the outset, it's a map from V into V double prime. Okay, you know that V is a linear space. Then we have something called phi of V, and you see that this map would give you a sort of, or what we expect is that phi is linear. So let us first investigate. So before that, we cannot expect this to be whole of V double prime unless we prove it. Okay. So let W be defined by the set of all Z belonging to V prime such that right? Okay. Therefore, we will so you see that phi is a map from V to onto W. The question that we want to ask is phi linear? So first let us resolve this. Okay. So let y of x be equal to, now zy equal to yx for every y belonging to a prime. Then let us compute this. Now we will compute this. Phi of x plus first additivity. This we write as this is equal to phi of why is this so? Let us calculate this. So this is actually zx that you have, and we want to verify this. Second one, we want to verify that phi of cx tilde equal to c times phi of x. This is what we want to do. Okay. Now this we want to prove for x tilde belonging to V. Here x tilde belonging to V and C belonging to . So let us prove this. So you see Z is equal to phi of Z of y equal to y of this is because we take if now this is equal to y of because y is linear. Linearity of y. Then you see that this is equal to z tilde of y plus because what we have is the association that x is associated with x tilde is associated with z tilde, y tilde is associated with, sorry, a second. Therefore, this is true, and that's equal to z tilde plus equal to and this is true for every y belonging to beta. Therefore, we have that is phi of x equal to phi of x tilde plus phi of x tilde or phi of this is equal to here of course we have z is equal to z tilde plus z double tilde. So this is correspondingly you have x equal to further let phi of alpha x tilde equal to z. Then zy is equal to y of alpha x and this is equal to alpha yx and that's equal to this is equal to alpha z of z tilde of y. This is equal to alpha z tilde, that is phi of alpha x tilde equal to alpha phi. Therefore, you see that phi is linear. Therefore, phi is from V to W contained in V double prime is everything. Still we have not seen or we have not shown that W is equal to W prime. What the question that you are asking is every element of V double prime generated by an element in V? Or is it possible to identify every element of V double prime with V? Let us now use that. Now you see, this shows that W is vector space over F and is a subspace of Now what about the dimension of W? That's what we want to do. Okay. So what about the dimension of? So let I am not using ZI deliberately. I don't know. Let me denote this because this is in say an element associated with Xi. Let us define this in this way. Now then we have Ij. So we are associating with each xj an element zi tilde. Okay. So this is the zi tilde phi of xk. This is what we are associating. Okay. Now we prove that so the first thing that we observe is that this is linearly independent. First thing. Is linearly. So let us calculate this. So suppose this is equal to 0. Is that it's 0 linear functional on V prime. Now let us compute this. So we have alpha 1 of y equal to 0 for every y. Now this is equal to sigma, because of the linearity, sigma alpha j zj tilde which is equal to this is equal to, by definition, y of sigma alpha j. This is 2.3. So y of this vector, this is a vector in V, is equal to 0 for every y, which we have earlier seen that y of x equal to 0 for every y, then necessarily x is equal to 0. Since are linearly independent, we have that is therefore, it follows that this is a linearly independent set in W. Therefore, dimension of W is greater than or equal to n. But W is in V double prime and dimension of equal to n implies dimension of W is equal to n. Therefore, W is an n-dimensional subspace of V double prime, where V double prime itself is n-dimensional. Therefore, this implies therefore, you see that phi is now it's an onto. It is enough to conclude that this is the phi is an isomorphism. Okay. Why? See, V double prime and V are of the same dimension. Okay, phi is a linear map, phi is an onto map, therefore phi is 1 2, and in fact it's quite now it is easy to, if you want you can verify this. It's quite easy. So phi is from E to E double prime, and what you have is phi of x equal to z is and only z of y equal to y of x for every y belonging to V prime. But z of y equal to y of x implies that let for every x for every y belonging to this implies z of y what I wanted to say was we wanted to prove the following, that what is phi of x is z. Suppose z is equal to 0, then z of y now what is z of y? And this we have seen that if y of x equal to 0 for every y, then this implies x equal to 0. Therefore, as a consequence of this result, this implies phi is 1 to 1. Phi is linear, phi is onto, phi is 1 to 1. Hence, but there is something very special about this isomorphism. But this isomorphism is natural in the sense that this does not depend on choice of any basis. So this is a very, very important thing. Because you see that the way in which we have defined is this. How are we associating x with the z? See, we have z of y is defined as y of x. We do not use any basis for the description of this. Then we say this is the identification, and nowhere in the definition we ever make use of any basis. Okay, why this particular remark? The reason is this: given any two vector spaces over the same field, of the same dimension of equal dimension, there exists several isomorphisms. For example, between V and V prime, one can define a number of isomorphisms. Okay? Whereas all of them are defined through some basis. Okay? So it really depends on the basis. So such isomorphisms in general depend on the basis. But here you have an isomorphism which is defined independent of the reference to any basis. And therefore this is something special, and this is what you call natural. So it's a natural isomorphism. And something very special. Or we say that V is identified. This enables us identify every element of V as an element of this is very important. shall use a slightly different notation. Let me make some statement about this. Define then we observe that the following, that is, since y is linear, x is also linear on y, so you get, we observe that alpha this is for alpha beta belonging to yeah, x prime belonging to v and y belonging to beta. Similarly, you have x this is equal to this is true for alpha beta belonging to x prime belonging to x belonging to v y tilde belonging to p prime. Okay, so look at this as a map. So this is a functional defined on V cross V prime. This is linear in both the variables. Keeping the other hence we say that this is a bilinear. Functional. Associated. Now what we have is the isomorphism that we have is this. This is the relation. We have x, y, we have, what is this? This is equal to y of x, this, and this we have identified with y of x is equal to z of y, which you write in the form using the same notation. Therefore, yz for x belonging to v, y belonging to v prime, so phi x is equal to z. Next. This is true for every y belonging to V. That means what? Where see, the important fact is that one does not have to consider V double prime separately. What is the reason? The reason is that it is naturally isomorphic to V, or V can be completely identified with V double prime in a very natural way. Okay? And it's also a unique type of identification. Therefore, V is the, we can say that V is the V double prime. Okay? So this you see, strictly speaking, what you have, once you have V, you have V, then V prime, these two are there, then you have V double prime, then you have V triple prime, etc. Okay? And you see that this is identified with this. What does it mean? That this becomes essentially this. And you see that this pairwise they are related, or it is essentially there are two vector spaces V and V prime, and V double prime becomes identical with V. So that's the sort of identification. Okay, fine. We also observe that xi yj is equal to delta ij, which is equal to yj zi. Where these are elements of script x, these are elements of script y, these are elements of script z. So script z See, this is the identification. So xi and yi are identified. There is nothing to distinguish between them. Okay? Right. So that gives. So what we see is that V double prime is precise in V, and this property is what you call reflexivity. Okay? That is, there exists a natural isomorphism between V and V double prime is what you call V is a reflexive linear space. Okay? So all finite dimensional linear spaces are reflexive. With this definition, by which the existence of the natural isomorphism that identifies V double prime now remark that we shall have all reflexive. One remark that we want to make is that this result is not true in general for infinite dimensional spaces. So this is not necessarily true for infinite dimensional spaces. Okay? In fact, you have problems with L1. So now we introduce another concept called annihilators. So Now let us start working on it. Let S be a non-empty subset now. Non-empty. Then we define the annihilator of S denoted by S superscript naught, or you call S naught, the set of all y belonging to V prime such that y of x equal to 0 for every x belonging to V. I am not assuming any structure on S, just assuming S is non-empty. Then we can show that the linear span or the annihilator of, or in other words, all those linear functionals which map elements from S to 0 is what you call annihilator. So what you have is this, there is V, there is V prime. Now suppose you have S here, then you have a subcollection here which we denote by S naught, such that if you take a y belonging to this and an x here, y of x so all the elements in S are mapped to 0. Okay. Now we first prove that the linear span of the null space of the linear span of S is also equal to S. Okay. So before that we make an observation. S2 both non-empty. Then we have S2 naught. That's quite easy to prove, because you start with an element of S2 naught. So every element of this maps all elements of S2 to 0, and trivially it maps every element of S1 to 0, and therefore such an element is certainly in S1 naught. So the relation goes the other way around. Okay. So if S1 is contained in S2, then S2 naught is contained in S1. So this is quite trivial. Just a statement would do. Now what we observe is this. See, S is contained in the linear span of S. Therefore we immediately have, which implies the linear span of S, the annihilator of the linear span of S is contained in the annihilator of S. Okay? The notation is this. Now take, we prove that so let y belong to S0, which implies y of x equal to 0 for every x belonging to S. But then you know that bracket S is the linear span of S. Therefore, this implies y of x equal to 0 for every x belonging to y, because any element of S is a linear combination of elements in S, and you know that y kills every one of x in S, therefore y kills any linear combination of that. Okay? Therefore, what does this mean? This implies so all those, every y that kills S is also kills every linear combination of elements in S. That means the linear span of, it is in the annihilator of the linear span of S. So we have now the statement, namely this is true. So we have proved that. Okay. Now what we want to observe is that, of course, clearly subspace of theta. That is obvious. It's very trivial to prove this. Now we want to do the following. So we want to investigate the relationship between the dimensions. That is the dimension of, suppose we start with a vector space, a subspace M of dimension M, and then look at the annihilator of that, which is a linear subspace of V prime, and then you want to ask what is the dimension of that. So the theorem that we prove is this. Let this we have assumed. This is equal to minus 8. Now this is quite easy to prove because we start with, so we start with a basis for, so let for M. Now what we do is enlarge a basis P. That is possible. Okay. Let be the dual basis. Be the dual basis. Such a basis exists. Now what we assert is the following. See, you have a V, now M is a subspace of that, then you have M naught here and elements of this is the situation. Equal to 0. This is the map that you have. So this is M naught. And you see that x1, x2, etc. xm is a part of M or it's a basis for M. Therefore, xm plus 1, xm plus 2, etc. xn belongs to this part. Somewhere here. It is not in M certainly. Okay? And what you have is there is a corresponding basis y1, y2, etc. ym, etc. ym plus 1, etc. yn. So that's a dual basis. So you have yi delta ij. This is the relationship that you have. Now what we claim is this. Yi of equal to 0 for I belonging to M plus 1 and J belonging to 1 to. This is what we make an observation. That's quite easy to observe. Okay, because this part we have split into two parts. All these maps, these to 0, these maps, these to 0. That is clear. Okay. Therefore, yi of yi belongs to M naught whenever I why is so? Why is it so? See, we have got If y is therefore y1 is a subset of M0, therefore the linear span of this then that means every linear span or the linear span of and this is a subspace of M0. Now we want to show that this subspace is essentially equal to this. Now you take any element what is it? We have proved that this is continuous. Choose any y belonging to okay. So you start with any element in M0. M0 is expand by exam. Therefore, y1, y2, etc. yn belongs to square. So what you have? You want to show that every element of M0 is okay. Suppose y is an element of this, then you see that this is equal to 0 for every x belonging to M. Therefore, y belonging to M0. Okay. Anyways, it's fine. Therefore, what we have is M0 is equal to span of which implies dimension of M0 is equal to n minus n. Let's start with so y is equal to alpha 1 y1 plus alpha m ym plus alpha m plus 1 y1 plus just compute this. Y of x1 equal to 0, y of x2 equal to 0, y of xn m equal to 0. What does this mean? This means y of x1 is y1 equal to alpha 1, etc. Y of xm is equal to alpha m, which implies, and each of this is equal to 0, and alpha 1 equal to 0, etc. alpha m equal to 0. Which implies y is equal to alpha m plus 1 or y is a linear combination of whenever y belongs to or this is equal to, so we get the result that follows is that it implies hence y, which in turn implies dimension of minus 6. Of course, these are linearly independent. That's about this. So that completes the proof of this. Now let us define m naught to be m naught. Therefore, m naught double prime, but which is isomorphic to B. Okay. Therefore, hence every element of m naught can be identified with an element of B. by the following: z of y equal to y of x, and z being identified with x, or z is equal to, here z belongs to v double prime, y belongs to y v prime, and x belongs to. So we have consequently the following here. There is a natural identification between M and M double prime. Okay. If M is a subspace of a finite dimensional vector space, V, then what? This is equal to M. In fact, this is the natural identification that we have. Okay. This is in fact the so you can, it's quite easy to prove. One can prove that M is contained in M double prime. Okay, so you take any x belonging to M, there exists a z belonging to, there exists a z belonging to double prime, such that x of y of x equal to z of y v prime. This is that. X belonging to M implies y of x or y of x equal to 0 for every y belonging to M naught. Okay, which implies z of y equal to 0 for every z belonging to which implies that is x belongs to therefore every element of So that completes the proof of M is contained in fact, this is an embedding. Okay. Now you see that the dimension of M naught equal to n minus n. But what about dimension of this is equal to n minus n by the definition, which is equal to therefore is n-dimensional. So that implies that M is equal to M double. So we just use a dimension argument to prove this. So you observe that the linear functionals over V prime are only those generated by the linear functionals over V prime are only those by elements of V. This is the important. You don't have anything else. So this is a representation for all linear functions on V prime is represented by elements in V. So let us look at one simple interpretation of this. Take V equal to R. Take V equal to R. Let us take the standard basis let V prime is equal to then what you have is if x is equal to x1 e1 plus e3, then f of x is equal to let A1 A2 denote FE2 and A3 denote E3. Then f of x equal to a1 x1 plus a2 x2 plus x3. Now consider the set of all x belonging to R3 such that f of x equal to 0. That is zero. You know that this is a plane passing through whose normal is given by which is equal to f of e1 thus every plane passing through the origin corresponds to a certain linear function. It's a linear function in the sense that its normal is determined by that's a very nice information. So in fact what you have is that you have take a plane passing through the origin so this is C3, this is I can write a better picture. Consider a plane passing through the origin. Now let this is a plane. So this is the plane that, so F E I is a norm. It's a normal. So this is what we call Fx. This is one axis, two axis. Okay. So that's an identification of the dual space, right? And it's quite clear that every vector in R3 corresponds to a linear function. That's why the dual of R3 can be identified with the R3 itself. Not the natural identification, but that really depends on what the basis that you choose. So since you have chosen here E1, E2, E3, get a certain numbers. But if you were to use another basis, then the representation is going to be different. Okay, thank you very much.